Hello everyone, welcome to ChemE-Shiksha. Today we'll be starting another most important topic from your interview perspective, that is heat exchanger. So today we'll be covering the types of heat exchanger and the flow configuration in heat exchangers. So before starting the heat exchanger, let me tell you about the mode of heat exchange. So we know there are three modes of heat exchange: conduction, convection and radiation. So the conduction equation or the governing equation for conduction heat transfer is the Fourier's law, that is Q equals to minus Ka dt dx, where K is called the thermal conductivity, A is the cross sectional area for heat transfer, and dt dx is the temperature gradient in the for the heat transfer. So the heat transfer driving force, we know that dt, the temperature difference, that is the heat transfer driving force. So why this negative sign? We know that the heat is transferred from the high temperature region to the low temperature region, and this dt is actually the final minus initial. So the final is actually the low temperature region. So that's why this negative sign comes to keep this q positive. So generally this conduction heat transfer describes the heat transfer through solid material. Now we have the convection heat transfer. The governing equation for convection heat transfer is the Newton's law of cooling, which tells us Q equals to H into A into Ts minus T infinite, where H is called the convective heat transfer coefficient, A is the surface area for convective heat transfer, Ts is the temperature of the surface, and T infinite is the ambient temperature, the fluid temperature. So this describes the convective heat transfer between a solid surface and the fluid which is in contact with that solid surface. Then we have the radiation heat transfer. The governing equation for the radiation heat transfer is Stephen-Boltzmann law, which tells that Q equals to sigma into A into Ts to the power 4 minus T infinite to the power 4, where sigma is called the Stephen-Boltzmann constant, and the value of this Stephen-Boltzmann constant is 5.67 into 10 to the power minus 8 watt per meter square into Kelvin to the power 4. So A is the area for radiative heat transfer, Ts is the surface temperature, T infinite is the surrounding or ambient temperature. So this governs the radiative heat transfer between surfaces. So you know that for radiation heat transfer there need not any medium in between two surfaces. There are also laws like Planck's law, Finn's displacement law, which are also used for specific cases of radiation. Now let us talk about the heat exchanger. What is a heat exchanger? Heat exchanger is a device which is designed to transfer the heat between two or more fluid, or between a solid surface and a fluid, while keeping them separate. The objective of heat exchanger is the efficient transfer of thermal energy or heat from one medium to another medium. Now the types of heat exchanger. Generally heat exchanger are two types, that is recuperative and regenerative. So what is the difference between these two, regenerative and recuperative? So recuperative heat exchangers utilize separate flow paths for each fluid which are exchanging heat across a wall. And for regenerative heat exchanger, actually they use a single flow path where the fluid alternatively flow and the heat is actually stored in the medium before being transferred. So this is the difference between the recuperative and regenerative heat exchanger. I am again repeating. So for recuperative heat exchanger, there are separate flow path of each of the fluid which are exchanging the heat through the heat exchanging wall. And for regenerative heat exchanger, the flow path of the two fluids are the same. The fluid will alternatively flow in the same flow path and exchange the heat, and the heat will be actually stored in the medium before being transferred. Now the recuperative heat exchanger are of two types. One is the direct contact type and another one is the indirect contact type. So the direct contact type means like the in case of cooling tower, one of the example for direct contact type is the cooling tower. So in cooling tower, the two fluids, the hot water and the cold air, they are in direct contact with each other. But in case of indirect contact type, there is not direct contact of the two fluids. So the fluid are separated by some wall and then it will be transferred through that wall. So indirect contact type heat exchangers are of three types: tubular heat exchanger, extended surface heat exchanger, and plate type heat exchanger. So tubular heat exchangers like double pipe heat exchangers, selective heat exchangers are there. Then we have the extended surface heat exchanger like the plate fin type or tube fin type, and the plate type like welded, gasketed, different type of heat exchangers are there. Uh, then flow configuration. So on the basis of flow configuration, there are three types of heat exchanger, or we can say also there are three flow configuration for heat transfer or heat exchanger. One is the counter current flow, another one is the co-current flow, or also called the parallel flow, and then we have the cross flow heat exchangers also. Now the next thing is the LMTD. So before starting LMTD, so the heat transfer equation, let me tell you, the heat transfer equation Q equals to U into A into LMTD. So if heat is transferred in between two points or between two medium or between two fluids, then the how much heat is transferred, that Q is equals to U, that is called the heat transfer coefficient, overall heat transfer coefficient U, into A, which is the heat transfer area, into LMTD. So LMTD is the logarithmic mean temperature difference. It is the logarithmic average of the temperature difference between the hot and cold fluids in the heat exchanger. So the delta TLM, the LMTD, is equals to delta T1 minus delta T2 divided by ln of delta T1 by delta T2. Now this is okay, LMTD, but why this LMTD? We also have the AMTD, that is the arithmetic mean temperature difference. That means the actual mean that we the difference between the two fluids, hot and cold fluid. But we don't take the AMTD or the arithmetic mean temperature difference. Rather, we take the LMTD or the logarithmic mean temperature difference. Why so? That means in this equation Q equals to U into A into LMTD, why we take this LMTD instead of directly taking the difference between the hot and cold fluid? So the reason behind this is actually, so if we see the temperature difference between the hot and cold fluid, this is not equal or not constant throughout the heat exchanger. That means, particularly if we talk about the parallel flow heat exchanger, so in that case, when the two fluid are entering in the heat exchanger, at that point the temperature difference between the hot and cold fluid is maximum, and when the fluid are exiting the heat exchanger, at that point the temperature difference between the hot and cold fluid is minimum. So if we want to take the temperature difference of hot and cold fluid, so which part or at which point we should take the temperature difference between the hot and cold fluid, that we don't know. So that's why it is more efficient to take LMTD, which exactly tells us the temperature difference between the hot and cold fluid, by taking the logarithmic mean. So then the heat transfer equation becomes more efficient. So that is the main purpose of taking the logarithmic mean instead of taking the arithmetic mean of this hot and cold fluid. So these are the flow arrangement in heat exchanger. So you can see this is the counter current flow where the two fluids, let's say this is the tube side and this is the cell side. So the two side fluids are, we can see properly, the two fluids are flowing in the opposite direction. That means if this tube side fluid is flowing from the left side to right side, the cell side fluid is flowing from the right side to the left side. So as these two fluids are flowing in the opposite direction, so this type of flow arrangement or flow configuration is called the counter current flow. Now in this type, where both the cell side and tube side fluid are flowing in the same direction, that is called the concurrent flow or the parallel flow. And then the cross flow, where the two fluids are flowing in perpendicular to each other. So you can see that this fluid is flowing in this direction, and this fluid is flowing in this direction, which is perpendicular to this fluid flow arrangement. Now the question is, which type of flow configuration is more efficient, or which flow configuration is better? The answer is actually the counter current flow configuration. So let's see in this graph. So in case of concurrent flow, as I told you, so when the hot fluid and cold fluids are entering in the heat exchanger, the temperature difference is maximum, and when they are exiting the heat exchanger, then the temperature difference between these two is minimum. So the variation of this temperature, hot and cold fluid temperature, is maximum throughout the uh, flow in case of co-current flow. But in case of counter current flow, the hot fluid inlet, this is the hot fluid inlet, this is the hot fluid outlet, and for cold fluid, this is the inlet, this is the outlet. So you can see the temperature difference between hot and cold fluid is almost equal. That means the temperature, the driving force is almost equal in each and every point. So that is one point. But the main thing why this counter current flow is more efficient than the co-current flow is actually the driving force. So one thing we can see from here, that the cold fluid outlet temperature, it is possible for the cold fluid outlet temperature to cross the hot fluid outlet temperature in case of counter current flow. But in case of co-current flow, it is not possible that the outlet temperature of the cold fluid is exiting the outlet temperature of the hot fluid. It is not possible for co-current flow or the parallel flow, but for counter current flow, it is possible that this cold fluid outlet temperature is crossing the hot fluid outlet temperature. We can see over here. So we know that Q, the heat transfer Q, equals to U into A into LMTD. So for LMTD is maximum or more for this counter current flow than the co-current flow or the parallel flow, because if uh, A, or the area of heat transfer, is same for counter current flow and co-current flow for both. Let's say we have two heat exchanger, for and for two of this case, the area of heat transfer is same. So if AC is equals to AP, that means the heat transfer area for counter current flow is equals to the area heat transfer area for parallel flow. Then also you can see that the QC will be more than QP, that is the heat transfer for counter current flow will be more than the heat transfer for parallel flow. So that's why from there we can tell that as U is same, because we are transferring the same fluid, so U is same, A is also same. So that's what that means, the LMTD is for counter current flow is more than the LMTD for parallel flow. So as the driving force is more in case of counter current flow, so that's why counter current flow or counter current heat exchangers are better or more efficient than the co-current heat exchanger or co-current flow. Okay, now let's see about the double pipe heat exchanger. So this is the diagram of a double pipe heat exchanger. This is the inlet pipe, this is the outlet pipe. So we have the two pipes, that's why it is called a double pipe. So this is the simplest design heat exchanger, simplest design possible, with two concentric pipes. One fluid flows inside the inner tube, and the other flows in the annular space between the two tubes. So this is one fluid. So you can see that this is called the tube side. So tube side fluid inlet, This is the tube side fluid outlet. This is the cell side fluid inlet. This is the cell side fluid outlet. There are some flanges. So this is the double pipe heat exchanger, which is the simple design, simple to construct and easy to operate. So double pipe heat exchangers are used when the heat transfer area is actually comparatively less. For small scale application, we generally use this double pipe heat exchanger. Heat transfer area can be increased by connecting them in series, but it will require more space as well as the pressure drop will be more because of more fittings. So we can increase the heat transfer area because generally it is used for small scale of application. That means when the heat transfer area is actually required heat transfer area is less, but we can increase this heat transfer area by connecting this kind of double pipe heat exchanger in series. But in that case, one thing that is this number of flanges will be much more, so the pressure drop across the heat exchanger will be more. And one thing, another thing is the space requirement will be more because we are connecting them in series, so that's why space requirement will be more. So that is another point. Now, it can't be used for dirty fluids as cleaning is difficult. So cleaning is difficult in this double pipe heat exchanger. So that's why it cannot be used for dirty fluid. But its advantages, it is simple to construct and easy to operate as well. Now next is the selective heat exchanger, which is the most important heat exchanger. It is most widely used heat exchanger in the industry. So this is the diagram. So in case of selective heat exchanger, we have the cell. Outside there is a cell, and we have the inside there is some tubes. So these are the tubes, you can see these are the tubes, and this is outside there is a cell. So this is the tube side inlet or outlet. This is the tubes, another let's say this is the tube side inlet, so this is the tube side outlet. So this is the pass partition or the partition plate, which actually in a divide these two part. So that means, let's say in this side the tube side fluid will inlet, okay, entering in this side, and it will flow throughout the tubes, through the tubes, and then it will come back here and it will exit at this point. This is the cell side part. So it might be inlet or outlet. There is another cell side inlet or outlet. So these are called the baffles. So baffles are actually to increase the turbulency, which will actually increase the heat transfer. The baffles also, they support the tube seat. Okay, they are the tie rods and spacers. We have the floating tube seat over here, and this is the self cover. Okay, this is the cell cover, and this is the floating head cover. This is the stationary head channel, and these are the support saddles. Okay, so this is the schematic diagram of selective heat exchanger. Now, so in selective heat exchanger, it involves two fluids at different temperature. One flows through the tubes, another flows through the cell. So it enables heat exchange across the tube walls. Typically, the higher pressure fluid is passed through the tubes. So it comprises of a cylindrical cell. Outside there is a cylindrical cell, and then inside there are some tube bundles, tube seats, channels, heads, and baffles. Materials like low carbon steel, stainless steel, and copper are selected based on pressure, temperature, and corrosion resistance. So based on which kind of fluid we are using, what is our operating condition like operating temperature and pressure. So based on that we select the materials for construction. So the advantage of using this selective heat exchanger is it has large surface area, and we can increase the number of tubes to increase the surface area. So the heat transfer, as the heat transfer area is more, so heat transfer will be more, so the more efficient heat transfer. So now it is suitable for a wide range of temperature and pressure, but limitation is its complex design and manufacturing. Then we have the extended surface heat exchanger. As I told you, the two types of extended surface: plate fin heat exchanger, another one is the tube fin heat exchanger. So plate fin heat exchanger, it consists of a series of flat corrugated fins spaced between the flat plates. So in between the flat plates, the fins are there, flat and corrugated fins are there. So fluid flows between the fins, promoting heat exchange through extended surface area. And in case of tube fin heat exchanger, the fins are attached to the outer surface of the tubes. So this is the difference between tube fin and plate fin. So in case of plate fin, the fins are in between the flat plates, and the tube, in case of tube fin, the fins are attached to the outer surface of the tubes. The fluid flows through the tubes and heat transfer occur between the tubes and fins. The advantage of this kind of extended surface is, so as the surface area is more here, so this fin arrangement actually provides large surface area, so that means the heat transfer will be more and efficient use of space due to extended surface. Then we have the plate heat exchanger. So it consists of multiple thin, slightly separated plates that have very large surface areas and fluid flow passages. It, its compact design is also one advantage, and also the high heat transfer efficiency. Fluid flows through the separate channels found by stacked plates, and heat transfer occurs through the plate materials. Plates are arranged to form channels for hot and cold fluids to flow alternatively. So these are some of the references, and thank you for watching this video. Please hit the like button if you like the video, subscribe my channel, share this video with all of your friends, and be a part of a growing network of future ready chemical engineers. Thank you all for watching this video.